chemical bonding in terms of orbital overlapping.
Let's take a look at an example. Oh, I have an example right here. If I were to ask you, hey, illustrate hydrogen gas, what are you going to do? I think a lot of you will do something like Lewis structure. Okay, H has one valence electron, another H has one valence electron, and on these two valence electron is going to be shared, just like what I have here. Okay, I think that's what you learned back in grade 10, or back in grade 9. You're going to draw two hydrogen Bohr model. Okay, two hydrogen Bohr model. One proton, no neutrons, and you're illustrating here that these two electrons are being shared. Okay? But in reality, or in the sense of the model that we know of called energy level diagram, is that really what happens? Because what really happens here, of course, is not just two electrons being shared like this, or having two electrons circled, illustrating that, hey, you know what, these two electrons, they're shared between two atoms. Well, you know what, in terms of the definition of a covalent compound or a covalent bond, yes, a covalent bond is when two atoms share two pairs of a pair of electrons, a pair of electrons, like we see here, like we see here. But what you need to know is that a bond is really more than just sharing electron. A bond illustrates an overlapping of atomic orbitals. Now, hopefully you remember what orbital was. Okay, we studied this, I think, back in October, in the beginning of October, looking at electron configurations, looking at energy level diagrams, and we say, of course, that each orbital is representing a certain shape, okay, a shape where electrons can be found. Hopefully you remember that. And hopefully, by looking at H2, we know that H has an electronic configuration of 1s1. Now, let's go back and review what that means. Okay, 1s1 means in the first energy level, in the S-shaped orbital, S stands for sphere, so this orbital has a spherical shape, you'll find one electron there. Okay, so hydrogen has one electron, we all know that. Where is that electron? Well, level 1 sphere, and that's where you'll find it. And to draw this, it is actually very simple to draw. Let me just illustrate this. So you have your nucleus right here, and you have your spherical orbital. Okay, in this orbital, you'll find electrons. Let me not draw the electron like this. There's electron, and this electron can appear anywhere. Okay, an instantaneous time, because electron doesn't stay in one stationary spot. They are allowed to move around inside this spherical orbital. But of course, there's only one. So to illustrate how bonding really works, let me just show you another hydrogen. Let me just show you another hydrogen using a different color. Here it is. Here's another hydrogen. Obviously, there is some sort of mode of attraction here where electrons, and this electron says, hey, you know what? We want to bond. Okay, we want to share our electron. By sharing our electron, we're not going to draw a line through this. We're not going to circle these two nuclei. That would be insane. But what you're going to see here is an overlap of the two 1s orbital. Okay, so that is something that I need you to start thinking about now, because we no longer want to talk about a line between two Lewis diagram. Okay, we want to talk about the blending, the overlapping of orbitals. That is how we illustrate a bond. Now, looking at the energy level diagram for hydrogen, we have, of course, 1s in its orbital box. There's 1 electron, and we have another 1s here with 1 electron. Obviously, to make hydrogen stable, or make anything stable, they want a full orbital. Okay, they want a full orbital. So to achieve that, these 2 electrons are going to be shared, and they're going to be shared under the confine of this blending or overlapping of orbitals. Okay, so that's how we're going to illustrate bonding now. So we're going to do a couple of more examples. We're going to keep it simple, okay, until, of course, we get a little bit more complicated by looking at carbon. So let's take a look at another example. Example 2. Okay, what we have here is HCl, hydrochloric acid. Okay, now, if you remember correctly, this is how you would draw the Lewis diagram for HCl. Okay, you have H sharing electron with the 7th, I guess, electron of the chlorine atom, but we all know that's not really the case. What's really the case is what I'm going to illustrate right here. Okay, hydrogen has this as an energy level diagram. We saw that before. Chlorine. Okay, chlorine is a bigger deal, but instead of showing you everything, I'm just going to show you what you'll see in your valence shell. Okay, so what you'll see here is 3s, that is full, 3p, remember the p orbital has 3 direction, and it's going to be 7. Okay, so most likely you're going to see this electron and this electron being shared, right? So this 1s electron and this 3p electron is going to be shared. Now, what about these guys? Well, we all know that these guys are not going to be shared. They're kind of like your lone pair here. All right? Because what chlorine wants to do? Chlorine wants to fill up its 3p orbital by having an electron here. What does H want to do? Well, filling up his orbital by putting an electron there. Okay, what better way to share these electrons just like that? But how are we going to illustrate this in a diagram? Well, let's draw hydrogen again. So we have hydrogen like this. Okay, now chlorine. This would be, chlorine is going to be big, but we're not going to draw the 1s, we're not going to draw the 2s, we're not going to draw the 2p. We're just going to concentrate on level 3. And if you think about it, in terms of bonding wise, the only orbital that wants to bond in chlorine is this orbital right here. These orbitals are not participating in bonding, so no need to illustrate them. This is the only one that is participating in bonding, and this orbital is a p orbital. Now, what p stands for? Well, some people say that p stands for propeller. And propeller looks like this. Okay? This is known to be the p y position. So I guess it would run along the y-axis maybe. Who knows? But that's really not an important point right now. Okay? All we know is it looks like a propeller. Now, again, what that means that electron has the ability to go and exist anywhere in this propeller. Okay? And guess what? When 1s and 3p wants to bond, they will do so by overlapping the 1s orbital and the 3p orbital. Okay, here's the overlapping, showing you the bond. Just like how we saw here with H2, the overlapness of the two 1s orbital. In this case, it's not a two 1s orbital, but a 1s orbital and a 3p orbital. overlapping, showing you the sharing of electron, just like how we would show you the sharing electron using Lewis structure. All right. So let's kind of go over some more example. We'll do another example, another simple example before we start looking at more complicated ones called hybrid orbitals. So example 3. Okay, let's do Cl2. Okay, so what do we have here? We have Cl bonded with Cl, and this is how we would illustrate that using Lewis structure. But we know that Cl, just like the last example, has a 3s full orbital and 3p orbital that has 5. Okay, so we want one more. But we have 2 3Cl. So let's do another one then. Okay, so as you can see, this and this wants to bond. Okay, this lonely electron want to get together and share their electrons, so both Cl will be full in terms of its level 3 orbital. This orbital belongs, of course, in p, so therefore it's looking like a propeller. Okay, this orbital right here is also a p orbital, so there's another propeller. All right, so I'm sure you guys can see that the two propeller will come together and overlap their orbital, showing you the illustrating the sharing of electrons. It's more like showing you the sharing of their orbital or electron cloud, whatever you like to call it. Okay, so hopefully you guys are comfortable with that. Hopefully, again, it's not that hard for you to figure out. Okay, all right, so let's look at something a little bit more difficult, because all 3 of these examples are relatively easy, because you can see, oh yeah, 1 electron, I want another one. In here, no, 1 electron, oh, I want another one. But what happens when the situation is a little bit more insane? Carbon is pretty insane. So let's take a look at carbon. Let's take a look at example 4. CH4. How are we going to illustrate that? Because this is actually not as easy to illustrate as you think. It's pretty easy when you're trying to do Lewis structure. Here you go, right? That's what we usually do. We've been doing these CH4 for pretty much a month now, looking at organic chemistry, but it really, in reality, does it really look like this? We know the shape of this is tetrahedral, but how are these sharing of electron came about? Let's take a look at carbon in terms of its energy level diagram. Carbon has a 2s. That's not, well, there's a 1s too, but we're not going to illustrate 1s2. We're just going to illustrate the valence electron, because only the valence electron participate in chemical bonding. And it's 2s2, 2p2. That's carbon. Okay? We know that hydrogen, and I know there's 4 of them, would have a 1s1. So looking at hydrogen, I need just 1 electron to share with. Okay, and just to let you know, there's going to be 4 of these things, because you're looking at CH4, right? Here it is. Okay, 4 hydrogen and a carbon. All right. Okay, I can see that there's a problem right here. If you look back into the last 3 examples, the blending, the overlapping of electron occurs in orbital that has 1 electron. These guys don't bond. We saw that with chlorine. Okay, only the ones that have one electron wouldn't mind sharing it with somebody else who also have one electron. So if you think about it, just think about it. Looking at carbon right now, do you see that there's only 2 bonding sites? I mean, yeah, these guys can share, these guys can share, but what about us? At the same time, even though when these shared, carbon is not full, carbon is missing 2 more electrons to be full. And you may be thinking, well, can both of these guys come in here? Or share, both of these are shared between this orbital? Now that sounds ridiculous, doesn't it? And it doesn't, that's not going to happen. So what's going to happen is this process known as hybridization. Okay? I know I see 2 bonding sites, but I'm going to do something where I'm going to get 4 bonding sites, because that's exactly what I need to do to make CH4. I need 4 bonding sites for carbon. How am I going to do that? For 2-step. First step is called promotion. What are we promoting? We are promoting a 2s electron, or okay, one of the 2s electron, and we're going to promote that to become a 2p electron. Okay, that's what we call promotion. So by doing that, you have this. Now you can see the fact that, oh, this looks much, much better. One of these per each of these, right? Not yet. Not exactly. Because if you think about it, it's not fair. Now, which of these guys will take the bullet and bond with an S? That's not fair. Okay? So what's fair is another step. And this step is a very important step called hybridization step. Okay? What do you mean by to hybridize? Well, to hybridize means to mix. What are we mixing? We're going to mix all 4 of these orbitals to become what we call a hybrid orbital. This hybrid orbital is level 2. Okay? This hybrid orbital consists of 1s orbital and 3p orbital, which we are going to call sp3 orbital. Okay, hopefully you know where sp3 is coming from. You know where the 2 is coming from. 2 stands for at level 2. People usually don't indicate this because it only happens in the valence orbital. It's not going to happen at level 1. Obviously, it's not going to happen level 3. This will happen at carbon's level 2. So most of the time you'll see sp3 being stated. Now, why sp3? Let me just show you in another color. Okay, the S came from this guy. The P3 obviously came from these 3 guys. Together, sp3. Okay, this is an sp3 orbital, and this sp3 orbital has 4 suborbital. Each suborbital has 1 electron. Okay? Because you can't just leave it as 2s1, 2p3. Because which one of these are going to take the 1? Right? That's not fair. So instead, mix this to become sp3 orbital. A brand new orbital. Now it's fair because each of these orbital will share with the hydrogen. This is going to be messy, but hopefully you get it. Okay. Let me just erase that for now. I don't want to. It's not something that nice to show you, anyways. So let's draw this. I want to really draw this. What do hybrid orbital look like? We know that s orbital looks like a sphere. We know that p orbital looks like a propeller. Okay, a hybrid orbital, hey, it's pretty nice. The straw carbon. This is carbon. Okay, at the level 2 state where the orbital is hybridized to become sp3. There's many ways of doing it. What I see most of the time is drawing it like this. Okay, that's an sp3 orbital, and there should be 4 of them. It really should be the same size. Okay, that's an sp3 orbital. Each orbital has 1 electron. So sp3, sp. So it's not a p orbital. Don't think it's 2 p orbital. This is 4 sp3 orbital, and each orbital is overlapping with hydrogen 1s orbital. Hey, look, I'm actually drawing the electron, which I haven't been doing. Okay, here's the blending. Okay, so if you look at many textbooks, when they draw CH4 under hybridized orbital illustration, this is what you'll see. Okay, and the theory behind that is that these are blending, and they have a type of bond. Okay, it's more than just calling it a single bond. We don't want to call it single bond anymore. Okay, we call this sigma bond. Okay, so these are all sigma bond. Sigma bond. Oh, that looks like a theta. That does not look like a sigma. Sigma looks like this, a little oval with a little thing on top. Okay, like that. That's a sigma bond. So a CH4 will have 4 sigma bond. All right. So really it's single bond, but later on we'll look at another organic molecule and you'll see some differences here. All right. So that's CH4. So I have a couple of more to show you. Okay, because so far what we've been doing is we saw single bond between S, we saw single bond between S and P, we saw single bond between P and P, and here we see 4 single bond, okay, between S and S3 and sp3. So let's take a look at example 5. For this example, we have C2H4. Okay. Now, if I were to ask you to draw C2H4, I'm sure a lot of you is going to give me something like this. Sometimes it's great to do this after organic chemistry. But yeah, that's C2H4. C and C is double bonded. Okay, each carbon is also bonded to 2 hydrogen each. How are we going to illustrate that? All right, before we even do anything, I think it's probably better that we looked at carbon in this in this energy level diagram once again. Okay, so at level 2, in the s orbital, there's 2 electrons. At level 2 in the p orbital, there's 3 suborbital. Each orbital has 1 electron. Okay. We actually have 2 carbon. So another carbon looking just like that. And then we have 4 hydrogen. just going to brush them up on the side right here, because we know how they're going to bond. We know how their s orbital is going to overlap with something. But what's interesting here is the carbon. We're going to have to somehow put them all together. But as you can see, how is that going to work? I mean, are these guys going to share? This guy's going to share? This guy's going to share? And these guys going to share? I mean, the hydrogens all have a place to go, but as you can see, there's a couple of empty orbitals here. This doesn't make sense. At the same time, we know C and C is going to bond. In fact, C and C is going to double bond. How are we going to illustrate that? Right? Now, the idea here is very simple. Take a look at this carbon. If I were to ask you, how many bonds is this carbon making? I'm sure a lot of you is going to say 4. 2 single bond, 1, 2, and 1 double bond. Here's your 4 bond, because carbon makes 4 bond. I've been stressing that for months. Here, it seems like carbon makes 2 bond. So again, we're going to do promotion. Followed by hybridization. But. We're not going to hybridize everything. Okay? We're not going to hybridize everything. What we are going to hybridize is just these 2. Okay, sorry. These 3. Okay? Now, you may be thinking, why do I want to do that? Why do I want to hybridize these 3? Well, let me show you. Okay, because we want to satisfy the fact that we want to create something that looks just like this. So we're just going to hybridize these 3. We're going to leave this as a p orbital. So let's do hybridization. Let me just draw that down. So this is what I'm hybridizing. Okay, so we're going to have level 2, sp3? No, sp2. And there's going to be 3 of these orbital. Okay, right? 1, 2, 3. There's going to be 3 of these orbital. Each of these orbital will have an electron right in its suborbital. Now, we're not going to disregard the p. We still have the level 2p. That's and its lonely electron. Okay, so that's going to happen. Now, that doesn't just happen to this carbon. Make sure we see the fact that it will happen this carbon as well. So this carbon will go through. Let me just erase all of this. Okay. This carbon will go through the same thing, okay, where you'll have promotion. And hybridize to give you, again, sp2 and a p. All right. Let's draw this. Let's draw this. Here's the carbon nucleus. Okay, there's going to be 3 hybrid orbital. Okay, there's going to be 3 hybrid orbitals. So remember, draw those hybrid orbitals and keep this bird in mind. You want to make sure that these electron cloud are as far away to each other as possible. So if you have 3 of these, I would advise you to draw it, I guess, I don't know, 120 degree apart. So you have one right here, right there, and right there. Okay, so these are sp2 orbitals. sp2, sp2, sp2. Okay, and guess what? you also have, let me draw this in green, a p orbital. That's a p orbital. Remember the propeller? Here's a p orbital. And you're not just going to have one of these. You're going to have two of these. Because for this carbon, you'll have something similar. And I'm going to draw it close because I'm going to show you right off the bat that this and this is going to bond. Okay? The two sp2 orbital is going to bond. Okay, they're going to form a sigma interaction. Okay, that is really showing you, what I'm really showing you right here is C bonded to a C. Okay, the C is bonded to a C via the blending of the two sp2 orbital. And of course, this guy also has a p orbital. Okay? Now, take a look at the carbon. Carbon and carbon is double bonded. Right? Carbon and carbon is forming double bond. But what you're illustrating here so far is just a single bond. Where's the other bond? The other bond lies over at the p orbital. Okay? So these p orbital are going to blend. Now, it doesn't look like they're blending. It looks like I'm just drawing something between them. But in reality, these two, if drawn properly, should overlap each other. And they don't just overlap each other one place. They actually overlap each other both places. Okay? Forming, I guess, two interactions. Now, we don't just call this the second bond or the double bond. We call these pi bond. So if you think about it, a double bond consists of one sigma bond and two pi overlap. So one sigma overlap and two pi overlap. Okay, that's what makes one double bond. So that's how we put carbon and carbon together via double bond. Now, I'm sure you guys understood the fact that there are two electrons here, two electrons on this side, and you still have to put in those hydrogens. So what you'll see here is an overlap of H orbital with the sp2 orbital. Okay, so that is actually what C2H4 is like. Okay, knowing that, okay, carbon needs to make a double bond with another carbon. A double bond means one sigma and two pi, so that's how we're going to do this. And then it's going to make two single bond with H, so make sure the hybrid orbital is bonded to the H. Okay, and it all comes down to knowing how to hybridize. So this step right here, knowing that I'm going to do this, is very, very important. Because if you were to leave it sp3, I mean, if you leave it sp3, I wonder how you're going to show double bond. All right. So I hope you understand, and I'm going to do one more example, okay, with you. And obviously, I'm going to show you a triple bond example. So example 6, C2H2. Okay, and we know that C2H2 is where in a situation you have carbon triple bond with another carbon, and each carbon is bonded to a hydrogen on each side. Now, how are we going to illustrate this? Again, let's go back to carbon energy level diagram. Again, we have 2 carbon. There it is. Okay, and once again, carbon is going to go through some sort of promotion, right? And the promotion is the same. Same promotion. Okay, now this is the tricky part. This is the part that I want you to maybe try to figure on your own. Okay, but if you don't want to, no big deal. I'm really gonna, it's not like I'm not gonna show you anyway, because I am gonna show you right now that how are you gonna hybridize this? Because what you're seeing here is a triple bond between the 2 carbon. Okay, how are we gonna illustrate triple bond? Because we saw how double bond is formed. So how are we gonna do triple bond this time? All right, let me just show you. If you want, you can pause this video and do it yourself. If not, just continue watching. I'll tell you right now that the hybridized orbital will be this 1s and this 1p. That's where the hybridization is going to be. Okay, so at level 2, the hybridization will be an SP1 or S1P1 or SP, right? And there's going to be 2 of these, leaving 2p orbital untouched. Okay, so we'll do the same thing for this carbon. We'll have a sp orbital and a p orbital here untouched. Okay, now it's time to draw this, right? So here's my carbon nucleus. I'm gonna have 2 sp suborbital, and so I'm gonna have one here. That's an sp orbital, and I'm gonna have one here. That's an sp orbital. I really should make them the same size, shouldn't I? Because why is one sp bigger than the other? I try my best. Okay, so that's 2 sp orbital. Then we have the p orbital, and there's actually 2 of them. Okay, we'll have this one right here. There's a p orbital. Okay, now we're going to draw another one. This is where knowing how to draw 3D is very important. I'm going to draw it like this. Okay, it's almost like this is coming out at you, and this is going behind my my whiteboard. Okay, and I'm going to draw another one. And by drawing the other one, I'm just going to simply overlap the sp orbital, showing you that yes, this carbon and this carbon is bonded through 1 sigma interaction. And yes, I'm going to have 2p orbital right here. Okay, beautiful. All right, hopefully you kind of understand right now why I chose to hybridize 1s and 1p. Okay, I hope you understand why. Let's put in those pi bonds. Okay, I'm sure you guys can see that these 2 are going to form a pi bond. Some people actually call it a pi bridge. Okay, they're going to form a pi bond. But remember, 1 sigma bond and 2 pi makes up a double bond. What about triple bond? Because this carbon and this carbon is going to be triple bonded to each other. This is really only showing double bond. Is there another pi bond that we can do? Or 2? course there is. Let me use a different color. Let me use pink. This and this is going to form a pi bridge. Okay, there you go. So when it comes to triple bond, you're looking at 1 sigma and okay, 2 more examples. So example 7. This one seems easy, right? Water. And to draw water, it's just like that. Oh, don't forget those lone pairs. Okay, without the lone pairs, you're not showing that oxygen is surrounded by 8 electrons, and that would be disastrous. Now, let me just tell you one thing here. The reason why I want to do water, which seems simple, is because it's not that simple. Because we haven't really illustrated lone pair, haven't we? Because for all the other ones, none of them had lone pairs. Well, chlorine had lone pairs, but we didn't really illustrate those lone pairs deeply for you to understand. Okay, because all we did was combining the p orbital and we just call it that. But it's a little bit more than that. Okay, so that's why I want to do a water example showing you how we're going to do the lone pairs. And how are we going to hybridize? Now, you may be thinking, why hybridize? Why hybridize? Because oxygen, in terms of valence, has 2 electrons on the s and 4 electrons on the p. Look, I can just bond these two to the 2 H's, right? H, 1s, 1. H is 1s1. Look. These come together, these come together, everybody's happy. Well, no, nobody's happy. Because are you telling people that this lone pair belongs to S and this lone pair belongs to P? Are you going to tell people that? Because as far as I'm concerned, these two lone pair have the same energy. If you were to say this one is this one and this one is this one, well, guess what? These two is more energetic than this one. That's not fair. Okay? How would you like it if I say that so-and-so is better than so-and-so? You won't like that, would you? Well, you might. It may be true. But you don't want to do that. You want to make sure everybody is fair. And I can tell you right now, not only are these 2 electrons under the same energy guideline, so are these. As in, all 4 of these are under the same energy level. They are. What that means is that we can't use 2s, 2p, and just bond these guys together and call it water. That's not the way it goes. There has to be some sort of hybridization that occurs where these electrons are all at the same energy level. Let's do promotion. So by promoting, we're doing this. Okay, so we have 2s with 1 and p each with 1, and the first 2 will have a 2. So we did that. Okay, that's a nice promotion. Now you may be thinking, do I have to do this promotion? Can I just, boom, right there, sp3? Because that's what you're going to do anyways, right? You're going to do an sp3. That way all 4 are under the same orbital umbrella, right? Why do I have to do this? Why can't I just skip the promotion step and say blend this sp3? There you go. Well, here's the problem. If you don't promote this guy won't want to hybridize. This is 2s full. Can't you see that this is very, very stable? As stability purposes, where S is already full, why would I want to hybridize when I'm already stable? Why do I want to go through the trouble of doing a whole bunch of these things when I'm all chill? Right? So that's why you want to promote this electron. Make him nervous. Right? That way hybridization can occur, or else hybridization is not going to happen. So promotion is extremely important, and you have to show this. All right, this is oxygen right now. Okay, it has 4 sp3 orbital. 2 of them is full. So these 2 are actually indicating these 2 lone pair. Okay, they're not going to participate in any bond. They're not sharing nothing with nobody. These guys are what's sharing, because these guys are not full yet, and they'll be happy to share with these hydrogen. Let's draw. Okay, so here's oxygen. Here's sp3. So all of these are sp3. All of these has electron. 2 of them are full. The other 2 has 1. And here's hydrogen. Oh, what am I doing? I don't want to put hydrogen there. That's ridiculous. Here's hydrogen. Okay. So that's water. Can you see the resemblance of this and this? Okay, these lone pairs are really part of an sp3 orbital, and the bonding here is the overlapping of sp3 and s orbital between carbon and hydrogen. Okay, so that's the reason why I want to do H2O. I feel the fact that we haven't seen a lone pair in action, so that's how you will illustrate a lone pair. All right. The last question is a very challenging question. So actually, it's not really that challenging. The trick here is this. The more you see this, the better you're going to get. Because the biggest question is, how do I know how to hybridize or what to hybridize? Well, for starter, it's really trial and error. As you get good at it and knowing for a fact that, okay, single bond is 1 sigma bond, double bond is 1 sigma and 2 pi bond, triple bond is 1 sigma and 4 pi bond, then you can start thinking about more complicated structure. So we're going to do one complicated structure, and then we're going to call it id for this extra unit, for this extra topic. So example 8. Let's see which one is nice to do. Huh? Oh, let's do this one. This one is nice to do. Formaldehyde. Remember him? The 1 carbon aldehyde, the stuff that preserved flesh. If we were asked you to draw this using Lewis structure, you would have given me this. Don't forget those lone pair. Oh, this looks like a heart. Looks like a heart. Don't want any hearts. There you go. This is what formaldehyde would have looked like. And how would you show this under the overlapping orbital? All right. First, we have carbon. Carbon's valence is 2s, 2p2. Okay? Let's not draw hydrogen. Let's not worry about hydrogen. Hydrogen is less to our worries because we have a lot more things to worry about, like oxygen. This is going to be 2s2, 2p4. Oh, what am I doing? 2p4. Okay. All right. Right off the bat, you may be thinking, oh my goodness. Without worrying about the H, how am I going to bond C and O together? Because C and O forms a double bond. Okay? O doesn't form bonds with anybody else. It will have 2 lone pair though. Carbon still needs to bond with 2 more hydrogen as we see here. I'm going to make this happen. Because how am I going to hybridize? Well, before hybridization occurs, let's promote first. Okay, so for carbon, we're going to promote this where every suborbital has one electron. For oxygen, we're going to promote this where two of the two p's will have full electron, and the 2s and one of the two p will have one electron. Now we're going to hybridize. The question is how? Should I make this sp3 or should I make this sp2 or should I make this sp? Well, take a look at this. It's always nice to know how to draw the Lewis structure because this gives you a lot of clue. Carbon makes 3 interactions. It makes 4 bonds, but 3 interactions. One with H, one with H, and one with O. Meaning that you're going to see 3 sigma bond coming from carbon. Now we've seen this before with C2H4, 3 sigma bond. How do we hybridize C2H4? Wow, that's right. It was sp2, right? Let's do that. Let's hybridize this to be at level 2 sp2. That's 3 orbital, each with 1 electron, and a lonely p orbital with 1 electron. Okay, because this will ensure that I will have 3 sigma bond right there, right there, right there. And this p can be a potential pi bond. I mean, I do need pi bond. Let's look at oxygen, because that's the killer. Okay, actually it's not really a killer. I'm sure you guys can figure it all out. Okay, now if you look at oxygen, oxygen is only bonded to one thing, and that's carbon, and it's a double bond, and nobody else. So if you think about it, oxygen will have a sigma and 2 pi. Sigma and 2 pi. Okay, how am I going to hybridize this to give me that situation? And which one to hybridize? Because am I going to hybridize these two? These two? These 3? All of them? Right? Now, I'm going to give you the answer. And again, this is all because of experience later on. Okay? You will know how to do this yourself once you see a lot more of this later on in post-secondary. I'll tell you right now that it's going to be these 3. It's going to be an sp2. Okay? At level 2, there's going to be an sp2. And this sp2 is going to have 1 electron in 1 orbital, and these 2 will be in the other 2 orbital. Okay, it's going to be full, and you're going to have 1 p orbital on its own, like that, which makes perfect sense because those p's right here are going to get together, right, and form pi's. These 2 most likely are those lone pairs, and this is the sigma that will bond with this sigma. You see how we did that? Okay, so it's very important when you hybridize, how many to hybridize and which to hybridize. Because if you look at O, I better have 1 sigma, 2 pi, and 2 lone pair. And this situation will give me that because these will be the lone pair. This will give me a sigma, and this will give me a pi. Let's draw. So I have carbon right here with 3 hybridized orbital. Okay, and a p orbital. Right? There's 1 electron here, 1 electron here, 1 electron here, and 1 electron there. And then I have this oxygen, okay, also with 3 hybrid orbital. Right here, and right there. Okay, how am I going to put in the electron? Well, I want to make sure that I have 1 here, so these 2 can bond. and I want to make sure that these are double ones. Okay, stemming from these two guys. There we go. And don't forget the pi. Okay. Now, we know that a double bond consists of 1 sigma and 2 pi. So let's draw that in. The bridge, the pi bridge. Okay. So here it is. Here's my double bond between carbon and oxygen. This right here is really showing you this, and it makes perfect sense that oxygen has these two lone pair we see here. The only thing left that we have to do is insert those hydrogen. Do we have a place to insert those hydrogen? Absolutely. Okay, they're going to be right here. Okay, so hopefully you see the resemblance of this and this. And again, I hope you later on would know how to hybridize these things. Now, as I said, you're not going to see this next year because you're not going to be taking chemistry next year. Okay, so the next time you see this most likely will be in university, in year 1 university, if you decided to do chemistry. Okay, the whole purpose of me wanting you to know all of this is because the regular grade 12 will get a glimpse of this. Okay, I'm not sure if they will go into that much depth, but they do have a glimpse of this, and they do know that bonding is really not just a stick between two atoms. It's really the overlapness of electron orbitals. Okay, and to stay competitive, this is something that I really, really want you to know.